Our sun is a solitary beacon of light and life in the blackness of space. But what if it is not alone? A shadow may move in the deepest dark, a hidden companion known as Nemesis. This hypothetical Death Star companion is a cosmic ghost, a theoretical object whose gravitational whisper could rewrite the entire history of our solar system. By the end of this, you will understand the profound forces that might secretly govern life and death on our planet. We will uncover why scientists propose this dark twin and explore the chilling evidence that suggests our world is subject to a celestial clock of destruction. What do you think is the most compelling mystery waiting in the outer dark? The hypothesis of a dark companion emerged from a startling pattern buried in Earth's own rocky history. In the 1980s, two paleontologists were studying the fossil record when they noticed something deeply unsettling. Major extinction events, the kind that wipe out vast swaths of life, seem to strike our planet on a regular schedule. Their analysis suggested a cataclysm visited Earth roughly every 26 million years. This was not a random series of disasters. It was a clockwork of death, a rhythm that demanded a cosmic explanation. Scientists reasoned that something must be disturbing the distant reservoir of icy bodies known as the Oort Cloud, sending a deadly shower of comets hurtling inward toward the sun. The most elegant and terrifying solution was a hidden star. This theoretical object was named Nemesis after the Greek goddess of retribution. Our own sun, the giver of life, could therefore have a dark twin, a Death Star whose distant gravitational tug periodically rains chaos upon the inner solar system. Every 26 million years, its silent orbit would bring it close enough to stir the outer darkness, triggering an event that could end civilizations before they even began. This rhythm of destruction presented a puzzle that only astronomy could solve. The fossil record gave us the when, but the vastness of space held the key to the why. The search for Nemesis became a grand piece of astronomical detective work, a quest to connect the dots between earthly death and celestial motion. The prime suspect was the Oort Cloud, a colossal sphere of icy remnants surrounding our solar system at a distance of nearly 1 light-year. Think of it as the solar system's deepest freezer, filled with trillions of frozen comets in a state of delicate gravitational balance. The theory suggested that a massive, unseen object was periodically diving through this distant cloud. With each close pass, its gravity would act like a stone thrown into a still pond, sending ripples of disruption through this frozen reservoir. Countless comets would be nudged from their stable orbits, some set on a long, falling path directly toward the inner solar system. This would create a comet shower, a storm of icy missiles with Earth right in the firing line. The challenge was identifying what kind of object could create such a predictable, long-term cycle. A planet did not have enough mass or reach. The gravitational culprit had to be something far more substantial. This is where the Nemesis star theory truly took hold. Astronomers calculated that a small, dim stellar companion to our sun, perhaps a red dwarf or a failed star known as a brown dwarf, could have a vast elliptical orbit. Every 26 million years, this dark twin would swing its closest to the Oort Cloud, unleashing its gravitational havoc before receding back into the interstellar dark. The beauty and the horror of this idea is its clockwork nature. It turns cosmic history into a predictable timeline where life's prosperity is merely the calm between catastrophic storms. But to prove a ghost exists, you must first find a way to see it. So what would this cosmic executioner actually look like? If Nemesis is real, it is no brilliant twin to our sun. Most models suggest it is either a dim red dwarf star or a failed star known as a brown dwarf. A red dwarf is the most common type of star in our galaxy, but it is also the smallest and coolest, glowing with a faint, deep crimson light. Its mass would be perhaps just a fraction of our sun's, maybe only a tenth or even less. This would make it incredibly faint, a mere ember in the vast dark. The other possibility is even more ghostly, a brown dwarf. These are celestial objects that never quite gathered enough mass to ignite the sustained nuclear fusion that makes a true star shine. A brown dwarf would be a cold, dark world, radiating only a faint whisper of residual heat, utterly invisible to ordinary telescopes. Its orbit would be almost unimaginably vast and stretched into a long, skinny ellipse. A single journey around the Sun could take 26 million years, a cosmic year so immense it defies human comprehension. For most of that eternity, Nemesis would be cruising through the deepest, coldest reaches of our solar system's domain, far beyond the scattered disk of the Kuiper belt and even the distant Oort Cloud itself. Right now, if it exists, it would be at the most distant point of its colossal loop, a dark sentinel hiding in the absolute blackness, waiting on the very edge of interstellar space. The Oort Cloud is not a place you can easily picture. It is not a flat ring like Saturn's, nor a neat belt like the asteroids. Instead, imagine a vast spherical shell of ancient ice, a cosmic deep freeze that begins where the solar system seems to end and stretches nearly halfway to the next star. This is the Sun's most distant territory, a gravitational reservoir holding trillions of frozen remnants from the solar system's violent birth. These objects, some as large as mountains, drift in an almost perfect stillness, their orbits balanced on a delicate gravitational knife edge. They are so far from the Sun that its light is just a particularly bright star in their black sky. This immense distance is what makes the Oort Cloud so stable and also so vulnerable. A slight gravitational nudge from a passing object is all it takes to upset this fragile balance. That nudge is the theoretical role of Nemesis. As this dark companion swings through its closest approach on its 26 million year orbit, its gravity would act like a deep, resonant drumbeat through the cloud. It would not simply push a few comets, it would send gravitational ripples through the entire shell, subtly altering the trajectories of countless icy bodies. Many would be flung outward into interstellar space, lost forever, but a significant fraction would be redirected inward, falling slowly at first, then with increasing speed toward the heart of our solar system. This is the genesis of a comet shower, a storm of icy missiles traveling for thousands or even millions of years before they reach the inner planets. The true danger lies in the sheer number of new orbits that cross Earth's path. With so many comets suddenly injected into the inner system, the probability of a catastrophic impact skyrockets. A single large comet striking Earth would release energy greater than all our nuclear arsenals combined, lofting enough dust and debris into the upper atmosphere to blot out the Sun for years, triggering a global winter that would collapse food chains and end civilizations. This is the chilling mechanism that connects a hypothetical dark star in the deepest dark to the fossilized evidence of mass death on our world. A single gravitational whisper from the edge of nothing could set in motion a chain of events that ends life as we know it. This rhythm of death is written in stone. The theory of Nemesis did not spring from pure speculation. It was born from a meticulous, decades-long study of Earth's own grim history, a pattern discovered by two scientists who dared to count the graves of entire species. Paleontologists David Raup and Jack Sepkoski spent years compiling a vast database of marine fossil records, tracing the rise and fall of life across hundreds of millions of years. As they analyzed this deep time ledger, a signal emerged from the noise. Major extinction events, the moments where global biodiversity plummeted, appeared to strike with a chilling regularity. Their statistical analysis pointed to a cycle of approximately 26 million years. This was not a gentle fluctuation. It was a pulse of destruction, a recurring catastrophe that seemed to reset the clock of evolution. The most famous of these events is the one that wiped out the dinosaurs 66 million years ago, the Chicxulub impact. A colossal comet or asteroid slammed into what is now the Yucatan Peninsula, carving out a crater over 100 miles wide and unleashing a firestorm that circled the globe. The resulting climate collapse ended the reign of the dinosaurs and paved the way for mammals to rise. This single disaster fits perfectly into the 26-million-year pattern. But it is not the only one. The fossil record suggests at least 5 other major extinction pulses align with this celestial timetable, each one leaving a distinct layer of iridium-rich dust and shattered ecosystems in the geological record. This cycle presents an almost philosophical problem. If the cause were something within our solar system, like a volcanic supercycle, the timing would likely be more random. The sheer regularity of these events points a finger outward toward the distant gravitational frontier, where a dark companion might be patiently keeping time. The hunt for this cosmic ghost required a new way of seeing. Traditional telescopes designed to capture the light of stars are nearly blind to an object as cold and dark as Nemesis. Its faint heat signature, a whisper of infrared radiation, was the only conceivable way to detect it. This challenge launched one of astronomy's greatest detective stories, a series of sky surveys using increasingly sensitive infrared eyes. The first major effort was the Infrared Astronomical Satellite, or IRAS, which scanned the entire heavens in the 1980s. It mapped the sky in infrared light, revealing a universe of cold dust and dim objects previously hidden. While it made monumental discoveries, it found no sign of a solar companion. The search continued with the 2-micron all-sky survey, which offered greater sensitivity, yet still the dark twin remained elusive. The most powerful hunt to date was undertaken by NASA, a wide-field infrared survey explorer, the WISE telescope. WISE was specifically designed to detect the faint glow of cool brown dwarfs. It conducted an exquisitely sensitive all-sky survey, peering into the darkest corners of our solar neighborhood. The data was painstakingly analyzed, searching for a slow-moving point of heat against the backdrop of the galaxy. The result was definitive and disappointing. WISE ruled out the existence of any object with the mass of a brown dwarf or a star within a vast volume of space around our Sun. It found no Saturn-sized object out to 10,000 times the Earth-Sun distance, and no Jupiter-sized object out to 26,000 times that distance. The data essentially closed the book on a classic Nemesis star. So why has this ghost proven so impossible to find? The primary obstacle is its profound darkness and incredible distance. Even at its theoretical closest approach, Nemesis would be an extraordinarily faint pinprick of warmth against an already cold and noisy infrared sky. Its motion would be agonizingly slow from our perspective, a crawl across the heavens over centuries, making it nearly indistinguishable from the fixed background of stars. Furthermore, the vastness of space it could potentially inhabit is staggering. Searching for Nemesis is like looking for a single, specific grain of sand drifting somewhere in the entirety of the Earth's oceans, while only being able to see a few miles in any direction. The repeated null results have forced a profound reconsideration of the entire hypothesis. If the clockwork of extinctions is real but the Death Star is not, then what other cosmic metronome could be ticking in the dark? The repeated silence from our most powerful telescopes points to a fundamental problem of scale and perception. Detecting Nemesis is not merely a matter of looking harder, it is a confrontation with the physical limits of observation. The core challenge is its profound darkness. If this object is a brown dwarf, it is a cosmic cinder, a failed star that never ignited. Its primary emission would be a faint whisper of infrared radiation, the residual heat from its ancient formation, now cooled to temperatures far below that of any ordinary star. Against the cold backdrop of deep space, this signal is incredibly weak, easily lost in the infrared glow of distant galaxies and even the warm dust within our own solar system. Compounding this is the sheer volume of space we must scrutinize. The potential orbital path of such a companion is not a neat circle close to the Sun, but a colossal, sprawling ellipse that could see it wandering tens of thousands of astronomical units away. Searching this volume is like trying to find a single, specific snowflake drifting somewhere in the air above an entire continent. You know it might be there, but you have no idea which way to look, and your tools can only see a few miles at a time. Then there is the problem of motion. An object so distant moves with an agonizing slowness across our sky. Its proper motion, the apparent shift in position against the fixed background of stars, would be minuscule over human timescales. From one year to the next, it might not appear to move at all, making it nearly indistinguishable from the millions of other faint, stationary points of light in our catalogues. We are searching for a ghost that not only refuses to glow but also barely seems to creep. These immense hurdles force a difficult question. Is our failure to find Nemesis proof of its absence, or is it simply a testament to the object's perfect camouflage, a hiding place crafted by the sheer, mind-numbing emptiness of the outer dark? The silence from our telescopes forces us to consider a different kind of culprit, one that is not a single object but the gravitational fabric of our galaxy itself. This is the galactic tide hypothesis, a compelling alternative that trades a dark star for the immense, rhythmic pull of the Milky Way. Our solar system is not static. It orbits the galactic center, but it also bobs up and down like a carousel horse on a merry-go-round, crossing the dense mid-plane of the galaxy roughly every 30 to 35 million years. This vertical journey places us in a region of space thick with gas, dust, and most importantly, a stronger gravitational field. As we pass through this dense plane, the collective gravity of all that mass exerts a tidal force on the distant Oort Cloud. This force is not from a single intruder, but from the entire galaxy. It is a cosmic squeeze, a subtle pressure that can dislodge comets from their stable orbits just as effectively as a passing star. The timing is strikingly similar to the extinction cycle, suggesting the real metronome of death may not be a hidden companion, but the grand ticking clock of our galaxy's structure. Another possibility lies closer to home, deep within the Earth itself. Some scientists point to our planet's own internal rhythms, a geological pulse of massive volcanic activity known as large igneous province eruptions. These are not simple volcanoes, but continent-scale ruptures that flood thousands of square miles with lava, pumping the atmosphere full of greenhouse gases and toxic particles for hundreds of thousands of years. The debate centers on cause and effect. Does an impact from space trigger these volcanic nightmares, or does the planet's own internal heat engine follow a slow, destructive cycle that poisons the climate from within? The evidence is complex and often contradictory, leaving us with a fundamental question about the source of these ancient calamities. Is the true danger a ghost in the outer dark, the rhythm of the galaxy, or a fire that has always burned in the heart of our own world? The idea of a hidden star plotting our doom was simply too powerful to remain confined to scientific journals. It quickly escaped into the wilds of popular culture, finding a natural home in science fiction. From novels to blockbuster films and video games, Nemesis has been reimagined as the ultimate cosmic antagonist, a literal Death Star whose arrival heralds the end of the world. This cultural fascination reveals a deep-seated human anxiety. There is something profoundly unsettling about the notion that our survival is subject to a timer we cannot see, set by a force we cannot control. It taps into the same primal fear that gave us myths of vengeful gods and apocalyptic prophecies. A scientific hypothesis became a modern-day myth because it offers a terrifyingly simple answer to the chaos of existence. Random disasters are frightening, but a scheduled cataclysm is existential. It suggests the universe is not just indifferent, but actively hostile, with a deliberate rhythm to its violence. Why does this concept grip us so tightly? Perhaps because it externalizes our deepest fears, giving them a name and a face, or rather, a dark, cold, and distant form. We are drawn to stories where the monster is not in the closet, but in the void, a celestial predator on a leash so long we only feel the tug once every 26 million years. This transforms our entire history into a mere interlude, a brief period of calm between the storms, making every achievement of civilization feel both precious and terrifyingly fragile. The true power of Nemesis was never just its gravitational pull on comets, but its gravitational pull on the human imagination. The name itself invites a dramatic comparison to that iconic battle station from a galaxy far, far away. The Death Star from Star Wars and our hypothetical Nemesis share a core, terrifying premise, a distant object capable of rendering an entire world extinct. Both are cosmic engines of annihilation, yet the mechanics of their destruction could not be more different. The Death Star is a weapon of intent, a technological terror that gathers immense energy to fire a single, concentrated beam, obliterating a planet in a blinding flash. Its threat is direct, instantaneous, and born of conscious malice. Nemesis operates on a scale that defies such drama. It is a force of nature, utterly blind and indifferent. Its weapon is not a laser but gravity itself, a gentle nudge delivered over unimaginable distances. That subtle push sets in motion a chain of events that might take thousands, even millions of years to culminate in a fiery impact. Where the Death Star represents a sudden, violent execution, Nemesis is a patient cosmic clockmaker. It does not aim, it merely stirs the pot of the Oort Cloud, leaving chance and orbital mechanics to decide which world, if any, will face the consequences. The Death Star's destruction is a spectacle, a fireball scene across a solar system. The destruction from Nemesis is a slow, creeping end, a winter that lasts for centuries, its true cause hidden in the deep freeze of space and time. One is a gun fired at point-blank range, the other is a single domino tipped in a line of billions, starting a fall that takes eons to reach its final catastrophic tile. A confirmed Nemesis would instantly become the single most compelling destination for a deep space mission humanity has ever conceived. Our robotic emissaries have traveled to every planet, but a journey to a dark stellar companion would be a leap into an entirely new class of exploration. The first step would be a dedicated probe, a vessel designed for a multi-generational voyage into the absolute cold. Unlike the swift flybys to Jupiter or Saturn, this mission would demand unprecedented endurance, traveling for perhaps centuries to reach an object that emits almost no light or heat. Finding it would be the first great challenge, requiring a new generation of space-based infrared telescopes specifically designed to pinpoint its faint thermal signature against the void. Once located, the probe itself would be a marvel of engineering, carrying instruments to analyze every secret this dark twin holds. Spectrometers would dissect its dim glow to determine its composition, revealing whether it is a failed star rich in lithium or a cold, ancient red dwarf. Magnetometers would map its invisible magnetic fields, and cameras would finally capture the face of this cosmic ghost, likely a world of swirling, deep crimson clouds or a barren, charcoal dark sphere. The scientific return would be immeasurable, offering a pristine sample of a class of object we have never visited, rewriting textbooks on stellar evolution and the very formation of our solar system. The existence of such a companion would force a complete re-evaluation of all long-term space travel routes. Currently, mission planners chart courses through a sun-centric system. But with Nemesis confirmed, every trajectory beyond the orbit of Neptune would have to account for the subtle but persistent gravitational pull of a second massive body. Its influence creates a dynamic, shifting map of gravitational wells and slopes. A planned century-long mission to the Oort Cloud, for instance, could find its path subtly bent, requiring constant course corrections or even utilizing the companion's own gravity as a slingshot for a boost into interstellar space. Nemesis would transform from a threat into a feature, a gravitational landmark in the outer dark that future navigators must learn to read like a star chart. This would open the ultimate new frontier, not merely a new planet but a new sun. Humanity would have to confront the reality of a binary star system, with all the profound implications for where life could arise and how planetary orbits remain stable over billions of years. The discovery would mark our graduation from a single star culture to a binary star civilization, forever changing our place in the cosmos. The search for a hidden gravitational puppeteer did not end with Nemesis. That same scientific impulse, the drive to explain strange patterns with an unseen mass, has resurfaced in a new and equally compelling mystery, the hunt for Planet 9. Far closer to home than the hypothetical Death Star, this potential world is thought to be a super-Earth lurking in the frozen expanse beyond Neptune. The parallels are striking. Just as the rhythmic pulse of extinctions pointed to a distant Nemesis, the peculiar, clustered orbits of a group of small icy bodies in the Kuiper belt suggest the hand of a massive, unseen planet. In both cases, astronomers are following the same detective's playbook, observing the effects of gravity on visible objects to infer the presence of an invisible one. The method is celestial forensics, reading the clues left in the motion of smaller bodies to build a case for a hidden giant. The motivations are also deeply similar, a quest for a grand, unifying explanation for the strange architecture of our own cosmic backyard. But could these two mysterious objects, one a potential star and the other a potential planet, actually be the same entity? The answer lies in the brutal mathematics of mass and distance. Planet 9, if it exists, is estimated to have perhaps 5 to 10 times the mass of Earth. That is a colossal world, to be sure, but it is a pebble compared to even the smallest star. A red dwarf, the dimmest true star considered for Nemesis, would be thousands of times more massive. A Planet 9-sized object simply does not possess the gravitational muscle to stir the entire Oort Cloud from its immense distance. Its influence is powerful enough to sculpt the orbits of Kuiper belt objects a few hundred astronomical units away, but it is far too weak to reach out nearly a light year and trigger comet showers on a galactic timescale. They are fundamentally different classes of object, one a possible rogue planet from our solar system's youth, the other a potential stellar sibling from its very birth. Yet their stories are woven from the same thread, a testament to our enduring fascination with the shadows that may yet move at the edge of our sight. This ghost might be invisible, but it could leave footprints in the snow. Without a direct visual, astronomers turn to the next best thing, the subtle warping of space itself. They search for the gravitational fingerprint of Nemesis by watching how other, smaller objects dance to a tune we cannot hear. The most promising clues come from the frigid outskirts of our solar system, from a class of icy worlds known as extreme trans-Neptunian objects. These orbit far beyond Neptune, in the lonely, sun-starved reaches where the solar system begins to fray into the Kuiper belt. Their paths are long and looping, taking thousands of years to complete a single journey around the sun. According to the theory, the immense gravity of a hidden stellar mass would not leave these distant orbits untouched. As Nemesis travels its own colossal loop, its gravitational field would act like a deep, persistent current in an ocean, herding these smaller icy bodies into a specific, predictable pattern. Instead of being randomly oriented, the orbits of these should show signs of clustering. Their points of closest approach to the Sun, their perihelia, might be grouped together in space. Even the angles of their orbital planes could be tilted in a similar way, as if they were all being gently pushed by the same unseen hand. Finding such a cluster would be like discovering a set of tracks in the mud, all pointing away from the same invisible predator. It would be powerful, albeit indirect, evidence that something massive is out there, sculpting the frozen frontier from the shadows. The search for this orbital signature is a monumental task of celestial cartography. It requires meticulously mapping the precise trajectories of these incredibly faint and distant objects, a process that takes years of painstaking observation. Each new etno discovered is another data point, another potential clue. Does its orbit fit the predicted pattern, or does it wander randomly, suggesting the dark shepherd is just a phantom? So far, the evidence remains tantalizingly ambiguous. Some studies have pointed to a possible clustering of orbits, a hint of structure that makes astronomers lean forward. Other analyses, however, suggest the data is still too sparse, the sample size too small, to confirm a pattern beyond statistical noise. We are essentially trying to discern the shape of a giant from the scattered footsteps of a few ants. The gravitational footprint of Nemesis is a whisper at the edge of hearing, a signal so faint it blurs into the background hum of the cosmos. Proving it requires not just finding a few strange orbits, but mapping an entire chorus of them, all singing the same silent song. Knowledge of the countdown would reshape civilization from the ground up. Our entire concept of time would expand beyond years and centuries to embrace the megacycle, a 26 million-year unit that dictates our species' ultimate deadline. Global culture would likely fracture into two dominant philosophies, the long now thinkers and the terminal generation celebrants. The long now would dedicate themselves to projects of unimaginable endurance, building archives designed to survive the coming fire, or developing space-based arcs to preserve Earth's biosphere. Their architecture would be monolithic and subterranean, cities carved deep into stable bedrock, designed as shelters not from war, but from a multi-century impact winter. Conversely, the terminal generation, those born in the final millennia of the cycle, might reject long-term planning entirely. Their art, music, and literature would be infused with a profound, bittersweet intensity, a cultural flowering born from the certainty of an ending. This would not be a panic, but a calibrated acceptance, a global society living with a celestial sword of Damocles. Our relationship with the sky would transform from one of wonder to one of vigilant watchfulness. The heavens are no longer just a beautiful mystery, they are a shooting gallery. Every new comet discovered would be tracked with paralyzing scrutiny, its trajectory analyzed to see if it is the one, the herald of the cycle's completion. This constant, low-level anxiety could forge a global identity unlike any other, uniting humanity under a shared cosmic vulnerability. Our drive to explore space would become a desperate race for survival, not just for knowledge, but for an exit strategy. The discovery of Nemesis would force upon us the ultimate question, not just how to live, but how to live meaningfully when the calendar has a final, inescapable page. This cosmic clock of extinction forces us to confront a terrifying possibility about the silence of the universe. The famous Fermi paradox asks a simple, haunting question. If the universe is so vast and old, teeming with billions of planets, where is everybody? Why have we found no traces, no signals, no evidence of other intelligent civilizations? One dark answer is the concept of a great filter, a barrier so formidable that it prevents life from advancing to an interstellar stage. A phenomenon like Nemesis could be the perfect candidate for such a filter. Imagine a universe where binary star systems with dark, lethal companions are common. In each of these systems, life might arise repeatedly on orbiting worlds, evolving over millions of years toward complexity and perhaps even intelligence. But just as a civilization approaches its technological zenith, just as it might be on the verge of looking outward to the stars, the celestial clock strikes zero. The dark companion makes its close pass, stirring up a cataclysmic comet shower that rains fire and ice upon its planetary children. The civilization and most of the life it shared its world with is utterly erased. The slate is wiped clean and the evolutionary clock is reset to zero. This cycle could repeat every 26 million years, forever trapping life in a loop of birth, blossoming, and annihilation. It offers a chillingly elegant solution to the paradox. The cosmos is not empty of life. but rather it is a graveyard of civilizations that never made it past their local periodic apocalypse. We are not alone in the universe because we are special, but simply because our solar system's own executioner is, for now, at the far end of its long leash, granting us a temporary and perhaps fleeting reprieve. The immediate blast is only the beginning of the horror. A direct comet strike would unleash a firestorm and a global earthquake, but the true planetary killer is the long, silent winter that follows. The impact vaporizes rock and hurls colossal quantities of dust and soot high into the stratosphere, where it forms a shroud that can linger for years. Sunlight is blocked and global temperatures plummet. Photosynthesis grinds to a halt, collapsing the base of the food chain. This is an impact winter, a famine that unfolds on a planetary scale, where the survivors of the initial cataclysm slowly starve in a frozen twilight world. Yet the devastation can amplify itself through the very ground beneath our feet. The colossal seismic shockwave from a major impact does not just shake the surface, it travels deep into the planet's mantle. This sudden planetary-scale trauma can rupture the thin, brittle crust in vulnerable spots around the globe. It is like striking a gong, the vibrations traveling through the entire structure to ring its weakest edges. These ruptures can trigger or massively amplify a large igneous province eruption, a geological nightmare where the planet literally tears itself open. Not a single volcano, but a continental wound that spews lava for hundreds of thousands of years, releasing toxic gases and carbon dioxide on a scale that dwarfs all human industry. The initial impact winter caused by dust would then give way to a suffocating greenhouse inferno. The climate is caught in a vicious whiplash, first frozen, then baked, creating conditions that are utterly unsurvivable for most large life forms. This 1-2 punch of impact and eruption is likely what sealed the fate of the dinosaurs. The Chicxulub impact crater in Mexico coincides almost perfectly in time with the Deccan Traps, a massive volcanic province in India that flooded an area the size of France with lava. Did the impact cause the eruptions, or were they a tragic coincidence? The Nemesis hypothesis suggests a terrifying answer, that every 26 million years, the solar system itself conspires to deliver not one, but a series of these double-barreled catastrophes, systematically resetting the planetary clock and leaving a scar upon the geological record that we are only now learning to read. Our failure to find this cosmic ghost with current tools does not mean the hunt is over. The next generation of astronomical observatories, now coming online or in advanced planning, are being built with the sensitivity to see the unseen. These are not just better telescopes, they are entirely new classes of eyes, designed to probe the dark, cold frontiers of our solar system in ways we once thought impossible. The Vera C. Rubin Observatory, with its legacy survey of space and time, will fundamentally change the game. This facility will not take a single, deep picture of a small patch of sky. Instead, it will perform a continuous cinematic scan of the entire visible heavens, night after night for a decade. It will detect billions of objects, tracking their movements with unprecedented precision. For the Nemesis hunt, this is a revolution. The observatory's relentless survey will catch the faint, slow-moving pinpricks that previous searches missed. It is designed to find things that should not be there, mapping the subtle gravitational disturbances in the outer solar system by tracking the paths of countless distant icy bodies. If a massive object is herding them, the Rubin Observatory will see the pattern emerge from the noise, like spotting the wake of a submarine from the surface ripples. Meanwhile, in the cold of space, the James Webb Space Telescope continues its own deep reconnaissance. While not a wide-field surveyor like Rubin, Webb's incredible infrared sensitivity allows it to stare into the darkest voids and analyze the faintest heat signatures. It can characterize the coldest brown dwarfs, objects that would be invisible to any other instrument. If Nemesis is a failed star, Webb has the power to see its dim, deep crimson glow, finally giving a face to the phantom. Beyond light, we are learning to listen to the cosmos. Future gravitational wave detectors, like the planned laser interferometer space antenna, will sense the ripples in space-time itself. They are tuned for colossal events like merging black holes, but a large, moving mass in our own solar system would also create a subtle, persistent signal in the fabric of the universe. Detecting that signal would be the most direct proof possible, a confirmation written not in light or heat, but in the fundamental geometry of reality. The combination of these technologies means we are no longer just looking for a needle in a haystack. We are building a magnetic sieve that can systematically sift through the entire cosmic haystack, finding every piece of metal within it. Within the next decade or two, we will have either found the ghost or declared the haunting officially over. This is the final chapter of a century-long mystery, and the last page is about to be turned. The discovery of Nemesis would instantly shatter a foundational truth of astronomy. For centuries, we have understood ourselves as children of a solitary star, a single point of light nurturing a family of planets. Our textbooks, our models, even our cultural identity are built upon this sun-centric view. To confirm a stellar companion is to rip that page out and start the entire volume over. We would not simply be adding a new planet to the list, we would be reclassifying our entire cosmic neighborhood from a single star system to a binary one. This is a paradigm shift of the highest order, forcing a rewrite of every fundamental model describing the solar system's birth, its structure, and its ultimate fate. The very definition of home would expand to include 2 gravitational hearts instead of 1. This new reality would demand answers to questions we have never needed to ask before. How do planets form and maintain stable orbits in a binary system? Our current models of planetary formation are elegant narratives of dust and gas coalescing around a single, stable point of mass. Introduce a second, massive star with a wildly eccentric orbit, and that serene nursery becomes a chaotic dance floor. The gravitational tug of war between the Sun and Nemesis would have created a violent, unstable environment in the early solar system, likely flinging countless nascent worlds into the Sun or out into interstellar space. The 8 planets we see today would be the lucky survivors, the ones that managed to find stable orbits in a gravitational landscape dominated by 2 competing powers. Their current positions are not just a product of the Sun's pull, but a delicate compromise, a celestial treaty signed billions of years ago under the influence of a dark twin we never knew was there. This explains so many lingering mysteries, from the odd tilt of the solar system's plane to the strange, scattered orbits of objects in the Kuiper belt. They are not anomalies but fossils, the enduring signatures of a binary gravitational field. The implications for life are even more profound. The habitable zone, that Goldilocks region where liquid water can exist, is calculated for a single star. A binary system has a habitable zone that is dynamic, pulsing and warping with the long orbit of the companion. A planet like Earth might spend millions of years in a comfortable position, only to have its climate thrown into chaos as Nemesis approaches, and its gravitational and radiative influence subtly shifts the delicate balance. Our own planet's long-term climate cycles, the great ice ages and warming periods, might not be solely driven by Earth's own wobbles and tilts. They could be the faint echo of a second sun's rhythmic pull, a gentle breathing of the solar system we are only now learning to perceive. We would have to reconsider the very probability of life elsewhere in the galaxy. If most stars are in binary or multiple systems, and if those systems often contain a disruptive partner like Nemesis, then the window for complex, intelligent life to evolve without interruption might be astonishingly narrow. Our existence is not a given, but a fragile victory in a cosmic environment far more complex and dangerous than we ever imagined. The ghost's influence would not stop at the distant Oort Cloud. Closer in, the frozen disk of the Kuiper belt would also bear the scars of its gravitational passage. This vast ring of icy worlds beyond Neptune is not the serene, orderly place we once imagined. Instead of random orbits, astronomers are finding strange patterns, a peculiar clustering of paths that seem to point toward an unseen shepherd. The most compelling clue lies in the orbits of a handful of extreme objects, those with paths so long and stretched that they take thousands of years to complete a single loop around the Sun. Their orbits are not just elongated, they are tilted, grouped together in space as if huddling for protection from a common threat. The mathematics is clear. The probability of this specific clustering happening by pure chance is astronomically low. Something massive must be herding them, corralling their orbits into this strange alignment. This is the strongest modern evidence for a hidden gravitational puppeteer, but its identity remains a puzzle. Could this shepherd be the legendary Nemesis? The immense gravity of a stellar companion would certainly be powerful enough to sculpt the entire Kuiper belt over billions of years. Its periodic close passes would create a persistent, underlying rhythm of disturbance, a background hum of gravity that constantly tugs and twists the orbits of every icy body in its domain. We would see its signature not in a single odd orbit, but in a vast, coherent architectural pattern across the entire outer solar system. The Kuiper belt would be a fossilized record of this dark star's influence, its structure frozen in time. Yet the observed anomalies might also be explained by a different kind of ghost, one far smaller but much closer to home. A hypothetical planet 9, a super-Earth lurking in the dark, could also produce this orbital clustering through its own persistent, though weaker, gravitational pull. The great detective story now becomes a question of scale. Is the architect of this cosmic sculpture a failed star on a million-year journey, or a lone, giant planet adrift in the perpetual twilight? The answer lies in the details of the herding. A distant Nemesis would create a broad, sweeping influence, a gentle but immense pressure that affects a wide swath of the solar system's outer reaches. A closer-in Planet 9 would have a more focused, localized effect, like a wolf moving through a flock of sheep, creating a tight cluster of fear. By mapping more of these distant orbits with observatories like Vera Rubin, we will eventually be able to measure the precise strength and reach of this invisible hand, finally identifying the true nature of the shadow that shapes our solar system's edge. This knowledge would place humanity in an unprecedented ethical bind. Suppose our calculations revealed the precise date, perhaps a million years from now, when Nemesis would trigger its next comet storm. Do we have a right to know our own expiration date? And does the global public have a right to that terrifying truth? Announcing such a discovery could unleash a paralyzing global anxiety, a psychological burden carried across countless generations. The certainty of a distant, inescapable cataclysm might drain all meaning from long-term endeavors, crippling investments in infrastructure, education, and space exploration. Why build a cathedral that will be dust in a million years? Why strive for a future that has a definitive, fiery full stop? Society could fracture between those who choose willful ignorance to preserve daily joy and those who become obsessed with the celestial clock, their lives overshadowed by a doom they cannot outrun. Yet, keeping the secret poses its own profound moral hazards. A small, powerful group of scientists and leaders would hold the ultimate privileged information, creating a cosmic class divide. Without public knowledge, there could be no collective, global effort to find a solution. The very panic that authorities might fear could be the essential catalyst for our survival. Knowing the deadline could galvanize our species like nothing before, funneling our resources and intellect into a single, unifying project: planetary defense. The threat of Nemesis is not a single bullet, but a shotgun blast of comets. We would have a million years to develop the technology to spot those icy missiles early and nudge them off course using gravity tractors or targeted explosions. This long-term focus could spark a golden age of technological innovation, pushing us to become a truly spacefaring civilization capable of shepherding dangerous objects away from Earth. The ethical question boils down to a choice between the peace of ignorance and the power of fearful knowledge. Is it more humane to let humanity live out its days in blissful unawareness, or to burden every generation with a truth that could ultimately be its salvation? The ghost in the dark does not just challenge our science, it holds a mirror to our courage. To test the ghost, scientists build a digital universe. They turn to supercomputers, crafting intricate n-body simulations that model the gravitational dance of countless celestial bodies over billions of years. These are not simple animations, they are profound experiments in cosmic probability, running calculations that would take a human lifetime on a single machine in a matter of days. The core question is one of stability. Could a star with a wildly eccentric orbit like Nemesis actually persist for the 4.5 billion-year age of our solar system without tearing the entire planetary system apart? The simulations inject a hypothetical dark companion into a digital model of our solar system, complete with planets and a simulated Oort cloud of millions of icy particles. They set the program running and watch what unfolds over eons of virtual time. The results are both illuminating and sobering. Many simulations show that such a binary system is, in fact, dynamically possible. The planets can find stable, if slightly altered, orbits that persist for billions of years despite the gravitational tug of a distant sibling. This was a crucial first finding. It proved that the Nemesis hypothesis was not physically impossible. The solar system could, in theory, withstand such a partner, but the simulations also revealed a deeper fragility. The key lies in the initial conditions, the specific mass, orbit, and starting position of the Nemesis object. Small changes in these parameters lead to wildly different outcomes. In some runs, the dark star's gravity gently herds the Oort Cloud comets, creating the periodic showers that match the fossil record. In many others, however, its influence is far more violent. The gravitational perturbations are too strong, either scattering the entire Oort cloud into interstellar space within the first billion years, or destabilizing the orbits of the giant planets like Jupiter and Saturn, leading to planetary ejections and cosmic chaos. The virtual solar system simply falls apart. This creates a fine-tuning problem. For Nemesis to exist and create the specific 26 million-year cycle without destroying everything else, its orbital parameters would have to be exquisitely precise, a perfect celestial bullseye achieved by random chance. The probability of such a perfect configuration emerging from the chaotic early solar system begins to look increasingly slim. The supercomputers show us that while a ghost can exist in the machine, keeping it hidden and perfectly behaved for so long requires a series of cosmic miracles. Brown dwarfs are the universe's forgotten middle children, objects caught in the awkward gap between planet and star. They are the most scientifically compelling candidate for Nemesis because they are massive enough to exert a profound gravitational influence, yet dark enough to have remained hidden from us for so long. A brown dwarf forms just like a star from a collapsing cloud of gas and dust, but it simply does not gather enough mass to cross a critical threshold. In the core of a true star like our Sun, the immense pressure and heat ignite the sustained nuclear fusion of hydrogen, the process that creates light and defines a star. A brown dwarf fails this final exam. It may briefly fuse a rare isotope like deuterium, but this is a fleeting flash in the pan. Without a sustained internal engine, it cannot fight the long defeat against gravity and heat loss. It slowly cools over billions of years, fading from a dim red ember to a cold, almost invisible coal drifting in the dark. This is a failed star, a cosmic also-ran that never quite made the cut. Its mass is the key to its stealth. Ranging from about 13 times the mass of Jupiter up to 80 times, a brown dwarf is far too heavy to be a planet, yet far too light to be a true star. It occupies a gravitational sweet spot, massive enough to stir the Oort cloud with its gravity, but cold enough to emit almost no visible light, making it the perfect phantom for our cosmic mystery. We are only now developing the eyes to see these dim objects. For decades, brown dwarfs were purely theoretical. The first confirmed discovery did not occur until 1995. The challenge is that they are brightest in their unruly youth and fade quickly into obscurity. To find them, astronomers must search for their faint infrared glow, the residual heat from their formation. This requires telescopes that can peer through the obscuring dust of space and detect the subtlest warmth. Missions like the Spitzer Space Telescope and the Wide Field Infrared Survey Explorer have been instrumental in building a census of these nearby dark suns. They have found that brown dwarfs are far more common than anyone suspected, some even floating freely in space without a parent star. Many are within just a few dozen light years of us, meaning our solar system could easily host one of its own. The newest tools, like the James Webb Space Telescope, are revolutionizing the hunt. Webb's incredible infrared sensitivity can not only detect colder, older brown dwarfs, but also analyze their atmospheres. We are learning that these worlds are shrouded in turbulent clouds of molten minerals and possess weather patterns more violent than any gas giants. The more we learn about these failed stars, the more plausible it becomes that one could be hiding in our own backyard, a dark twin whose gravitational whisper has been guiding our history from the shadows all along. The idea of a solitary sun is actually a cosmic anomaly. Look up at the night sky, and most of the points of light you see are not single stars but binary or multiple systems, two or more stars locked in a gravitational embrace. Our sun, flying solo, is in the minority. If Nemesis were real, it would not make our solar system strange, but rather perfectly normal. We would simply be joining the galactic majority, a typical binary pair among billions. This shift in perspective forces a profound question about our place in the cosmos. For so long, we have considered our stable, single star system as a prerequisite for life, a quiet harbor in a chaotic universe. But if most stars have companions, then life, if it is out there, must be evolving in far more dynamic and complex environments. The existence of a dark twin would shatter the illusion that our cosmic address is special. Instead, it would become utterly ordinary. This realization carries a double-edged sword for the search for extraterrestrial life. On one hand, binary systems can have stable habitable zones, and planets are known to orbit double stars. Life could certainly arise there, but a system with a Nemesis-like companion introduces a terrifying variable, a built-in timer for apocalypse. The galaxy could be filled with worlds that repeatedly evolve complex life, only to have it wiped clean every few million years by a comet storm triggered by their own dark sun. This transforms the Great Filter from a single, mysterious barrier into a recurring, cyclical event. The silence of the universe might not mean that life is rare, but that intelligent life rarely, if ever, survives long enough to escape its own solar system's scheduled renewal. Our continued existence may not be a sign of our uniqueness, but merely a testament to our current position in the orbital calendar, a temporary piece in a galaxy that is far more prone to periodic chaos than we ever dared to believe. The quest for Nemesis began with a pulse of death in the stone, a rhythm of extinction that demanded a cosmic explanation. It propelled us on a journey from the fossil beds of Earth to the farthest, coldest reaches of our solar system, chasing the shadow of a dark twin. We built ever more powerful eyes to scan the infrared dark, and when they saw nothing, we sharpened our minds instead, considering galactic tides and planetary shepherds. The phantom star remains elusive, a ghost that has so far refused to be pinned down by observation. Yet the value of this great hunt is not merely in its final answer, but in the profound questions it forced us to ask along the way. In searching for one ghost, we have mapped the gravitational contours of our own backyard with unprecedented clarity, discovering strange orbital patterns and unexplained structures that continue to hint at hidden masses. We have been reminded that our solar system is a dynamic, evolving place, still capable of holding profound secrets. The mystery of Nemesis, even unconfirmed, has expanded our understanding of the dark frontiers beyond Neptune and transformed our view of Earth's place in a potentially violent cosmic clockwork. So we turn the question over to you. After this journey through the evidence and the emptiness, where do you stand? Do you believe our sun sails alone, a solitary beacon in the void, or is it part of a binary pair, its light balanced by a dark companion still waiting in the interstellar night? Share your thoughts in the comments.